Okay, so this EP, right, we will see the examples, right, how to use the techniques to test whether, right, our series is convergent or divergent. Okay, so let's start with the first techniques. Okay, if you have the summations, right, 1 over n times n plus 1. Okay, so if we use the limit of the am, so then we found that, right, this the value of the limit is equal to 0. Right? So we cannot conclude whether, right, if the limit equals 0, then our series is the convergent or divergent. Then we think about that if the term an, right, can separate in two terms, the difference of the two terms. Okay, so this equals n minus 1, right, minus n plus 1. Okay, so then we use the cancellation techniques. We have to find, right, then our objective would like to find the limit, right, of the term of the Sn. That means that we have to find what is the term of the Sn. So for to find the term Sn, we have to use the ideas of the inductions, that we have to find the term of the S1, S2, S3, right, and until we can write in the general formula of the term Sn. Okay, so S1, right, is equal A1, right, so the term A1, like if we write in the term of the 1 over n, right, minus 1 over n plus 1. Okay, so you got it, right, 1 minus 1 over 2, and the sum of the term S2, right, come from the term A1, right, plus the term A2. Okay, and the term A1 is equal 1 minus half, and the term A2 is also equal half minus 1/3. You can see that, right, it's just the conservation, and it's left that 1 minus 1/3. Okay, then you do the same with the term S3. It's come from the terms A1 plus A2 plus A3, and until they will just cancel, right, so it's left that 1 minus 1/4. So we can predict that, right, the term Sn is come from the term A1 plus A2, right, until the term An could be equals 1 minus 1 over n plus 1. Okay, then we would like to find the limit of these terms, which also equals 1 minus 0, which also equal 1. Okay, so if the term limit of the term Sn exists, so we can conclude that our series is also converged, right, and the summations, right, or the results of the series, right, is also equal as, I mean, right, is also equal to the limit of the term Sn. Okay, so this is the first technique, right, and if the limit, or we can check whether if the limit of the term Sn is equals, for example, like positive infinity, right, we also can conclude that, right, our series also divergent too. Okay, so this just use the first techniques or the cancellation techniques to check whether our series is the convergent or divergent. Okay, so then we have to compare with the geometric series and the P series, right? Can you remember the geometric series? We write in the terms of the A1, right, time with the R is the common ratio, right, in the geometric sequence, and to the power of the n minus 1. Okay, so if this converge, right, and then the summation is also equals A1, right, over 1 minus r. This is the term of the sum. This occur, right, when the value of the term r is absolute r less than 1. That means that, right, the term r is between negative 1 and 1. And also if the absolute r less than 1, right, so you also answer that, right, this is the value of the sum, and also that your series is also converged. And if the opposite like this, that means, right, if the absolute r, right, greater than 1, that means that, right, the value of the r greater than 1, right, or the value of the r less than negative 1, right. So this term we got that, right, our geometric series also diverge. Okay, so the opposite of this one, so we have to include other 1, 2. Okay, so this is compared with the geometric series. And then when compared with the P series, the P series is the term order summation, right, 1 over n to the power of P. And then if we compare with the term P, okay, so if the value of the P is greater than 1, right, or P is the less than, okay, it's opposite to the geometric series, right? So if P greater than 1, right, then the P series is also converged. Okay, and if P less than or equal 1, right, then the P series is also diverged. Okay, so for examples, if we have the sum of the geometric series, for example 1 over 2 to the n, okay, right, and then plus 1 over n square. Okay, so you have, this is the summations between the geometric series and the P series. Okay. So we have to distribute this term, so you got that, right. The first term is the P series. Oh, sorry, this is the geometric series. So this is also equal the summation of the half to the power of the n, right? Since the n to the power, since 1 to the power of the n also equal 1. Okay, and this is the geometric series, which is the term r is equal half with than 1, right? So this term you also got that. This term is the converge. Okay, and then the second term, this is also the P series, right? When P is equal to, which is the greater than 1, so this also converge. Okay, so when we find, right, the sum, the converge, right, plus the series is also converge. Okay, so you get the converge. Okay, so if one term is a diverge, okay, the other is also converge, so this also diverge. Okay, and the last case, which we don't know, right, is the diverge or converge. We have to check that all term this. We can conclude only converge plus converge, you get converge, right, and converge plus diverge also diverge. Okay, okay, so the next, if you like to use the test of the divergence, for examples, summations, what else? Okay, for example, right, n cube over 2nq plus 1. So this is the term of the term an. Then we have to find, right, the limit of the term an. Okay, then we got that, right, limit of the term an, right, it's equals, so easier, right, the top terms and the bottom term, the highest degree, right, of the top term you get the same degrees, right, then the our limit, right, just divide by the highest degree, so we got that, right, 2 plus, which this term the limit also close to 0, right, then you got that, right, the value of the limit is equal half, that not equal to 0. So then we can refer the theory of the divergence test. We also got that, right? Our series is also divergent, right? Okay, so not difficult, eh? Just like simple examples. So okay, so I think in the integral test you just practice in your homework. It's quite more step, right, to show. So your answer, right? For example, right, if you have like a summation of the 1 over the 4th root, right? This is 4, right, of the term n, or we can write that, right? 1 to the n to the power of the. So this is the p series, right? P is a quarter which less than 1. Then we can conclude that this series also diverge. Okay, so just the p series, right? So you have to check that can refer from the p series. You can answer that converge or diverge, right? Just like that. The reasons is only one sentence. Okay. But it's opposite, right? Be careful if we write in this term, right? N to the 4. This is also the p series, but p is equal for which greater than 1, right? So this series is also converged, right? Just different. Okay. Anyways, right? If you would like to prove this, you have to use the integral test, right? But we can refer from the properties of the p series. Okay. So what else? Let's see more about the so I think this is also more complicated. Like to show about to use like the techniques of the squeeze theorems, right? Between what else? Okay, so if we have like summations, right, of the size n, right, over n squared. Okay, so the value, right, you know that, right? The absolute sign, right, is also less than or equal 1, right? Since the value, the term sign is greater than or equal to -1, right? And less than or equal 1, right? So absolute sign less than 1. And then we divide by the n squared, so we have to use the comparison test, okay, for this term. We found that this is the p series, right? Which the value of p is equal to which greater than 1, right? So this series, right, is also converged. And one thing that we have to find, right? So this we have, before use the limit comparison test, right? You have to make sure that, right, your term is 0. So we will find, right, the summation of the absolute this term, which this term, right? And then we got that, right? When we compare, right, the comparison test to this term. This term is also the term, right, absolute sign n, right, also less than or equal this term, and this term is converged, right? Then we can conclude that this also converged. This term are also converged, okay? And but this is the absolute sign, right? So then we got that without absolute. Also converge, and it's the kind of the absolutely convergent too. Okay, that's all. Use the comparison test. What else? When we have to find about it. Okay, let's see. Let's see more. If you have okay, when we ready summation, right? N over n plus 1 to n squared. Okay, so this is in the terms of the power, right, of the n squared. Then think about the root test. Okay, so we have to find the n root of the absolute. So if we take, right, the n root, so this is equals, still have in this term, which the limit of the n over n is equal 1, right? And to the power. This is the third type of the orbital rules. So we have to let that change this term in the term of the. And then we take the natural log, right? Take 1 to help solve. And then when we take the limit of this term, and then we found out this is log 1 is also equal to 0, right? And then this is in the indeterminate form of the infinity times 0, right? Then we have to change if we want to use the orbital rules. Right? Easier, right? Just change x to be the denominator, right? So it's easier, right, to find the derivative, right, more than to change the term of the 1 to be the denominator. So this is the indeterminate form, right? 0 by 0. Now we can use the orbital rules. Okay. Then this equals, or is to be in the term of the x. Okay. Okay, you have to find, right, the derivative of the 1 equal the 1 over this term. And then time the derivative inside, which you have to use the quotient rule, right? Can you remember? So d GOV, right? It's equal v du, right? Minus u dv over v squared. Okay, so this is the quotient rule. So this also equals v, right? Time with the term derivative of the top term is equal 1, right? Minus u dv. Okay, and then divide by the bottom term square. And also, right, the derivative, right, of the 1 over x equal 1. Okay, then some terms can cancel, right? This term and this term can cancel. What else? Okay, so this term, right, x and x squared. Okay, so this you got that, like x and negative x can cancel. So it's left that equals, right, the limit of the term is equal 1, right? But this is the negative 1, so this also equal negative x, right, over x plus 1, right? So this also equal the negative 1. Okay, but this is the limit of the 1, right? So you have to change that. So the limit of the term of x, right? So when we take, so this is equal to e to the negative 1, right? Or 1 over e. And what else moment, and okay, so the 1 over E, okay, E is approximately 2.7, right, which more than 1. So 1 over E is also less than 1. Then from the properties of the root test, when the limit is less than 1, is also converged, right? So this term you can answer that, right? So this the sequence, this sequence, right? Sorry, this series is also converged. Okay, series is also converged. Okay, so this is right. You got that, right? This is converged. Okay. Okay, so you can practice more, right, and see the other technique like when you have about the factorial, right? Think about the ratio test, but you have the property like the root test. When your limit is less than 1, it's a converge, and also absolutely converge too. And when the value of the limit greater than 1, right? So you get that, right? The series is also diverged. But if it's equal, right? Just you cannot use root test or ratio test. Have to use the other methods, right, to test that. Okay, so I think now we have more time to finish this EP like this. Then we continue to the next EP. Bye bye.